Hi everyone, I hope you're doing well. Today we're going to continue our discussion of diodes, okay? And we're going to focus on two things. Figuring out what the built-in voltage in a diode should be and how it varies with temperature, because it does. And we're going to figure out how the current through a diode should depend on voltage, what's called the Shockley equation, okay? So I'm going to go over to the notepad now and we'll look at an outline and then we'll get to started on our discussion. Okay, we've been talking about diodes, and last time we talked about them using the depletion approximation, which gives a good physical picture of the diode. You have the N and P-type semiconductors, and then at the junction you have this depleted zone where there are very few free carriers, and that seems to control the behavior of the diode. We saw how it can shrink or grow depending on the voltage that you apply across the diode. Okay? But today, we're going to look a little more closely. And we're going to talk about some effects that depend on temperature. So it turns out we have to do this in order to really figure out what the built-in voltage across a diode should be, and to describe how the current through a diode should depend on the voltage across it. So that's what we'll do. Now, because of this, we're going to have to bring in some thermodynamics at a couple of places. Well, I'll try to explain what we're doing really clearly, but you'll find that if you've had statistical mechanics, that it should all make sense. And if you haven't had statistical mechanics, there are some things you're just going to have to take on faith, okay? But we have to talk about these things in order to describe these interesting physical devices. I still want to talk about diode devices, the important technology that's built out of diodes, LEDs and solar cells being the most important examples. I think that's probably going to end up, not today, but in the lecture that follows, but we haven't forgotten about it, okay? Well, let's hang on here, and then we'll continue. Okay, so let's focus now on the built-in voltage. Okay? Now, just to be clear about what this is, let's make a little drawing of our PN junction inside of a circuit. Oops. Oh my gosh. Hang on one second while I would make my drawing. Okay, there we are. So we have a PN junction, and then the device is connected to a battery, okay, a voltage source. Now, we know that if we apply a voltage in the forward direction, that at some point current will start to flow, okay? And we can imagine in a diode that the current turns on rather suddenly at a threshold voltage, okay? In the depletion approximation, it's the point when the width of the depletion layer goes to 0, okay? We'll see when we look more closely that that's still true, but actually the transition is a little bit not quite as sharp as the depletion approximation makes it seem. But I'm getting off topic. In any event, let's imagine that we hook this up and we slowly increase the voltage in the forward direction until current just starts to flow through the device. Okay? So here I've shown the direction of the electron motion through the device. And this should start to happen. Current should start to flow when the voltage equals the built-in voltage across the junction. Okay? So V built in is the voltage required to reach forward bias, where the diode starts to conduct. Okay? At that point, the work required to take an electron around the circuit from the P side over to the N side and inject it into the semiconductor, that work is just E times V built in. Okay? And we'll write it this way. We'll call that work delta mu. And this is a work per electron, the minimum work per electron to take an electron around the circuit from the P side of the semiconductor to the N side. Okay? All right. Now, if we were at T equals 0, this would be very clear. The work required, I'll just write it as W for a moment, would be equal to the change in potential energy of the charge. Okay? Seems straightforward enough. And the change in potential energy then would be, for each electron, would be equal to the band gap of the semiconductor. Okay? So we would expect that in this case, the work per electron would be equal to the band gap energy of the semiconductor, since after all, we're taking the effect of our motion is to take an electron from the lower band in the semiconductor and deposit it up in the upper band on the N side, okay? And so this would mean that V built in should be equal to Eg divided by the charge. That's what we would expect in the low temperature limit, okay? Now, that's all well and good. But what's interesting is that as you raise the temperature, so for temperatures that are greater than 0, the work per electron gets smaller. Okay? And that's something we'd like to explain. And here, I'm actually going to show you a demo of this if you'll hold on. One moment. Okay, here's my demo. I have a diode, a silicon diode, that's attached to a digital voltmeter. And the voltmeter has been turned on to the diode check setting. And what it does there is it applies voltage, and it increases the voltage until the current reaches a certain value, very, very small value, like 1 microamp. So this is the voltage required to get a very small current to flow through this diode. It's 0.606 volts, okay? Now I said that at low temperature, the value of this turn-on voltage should be equal to the band gap. And let's check it out. So I'm going to cool my diode down with some liquid nitrogen. It won't cool to temperature 0, but it'll get most of the way there. It'll cool to 77 Kelvin. Okay, you ready? Okay, so the voltage we measure now is I think it's 1.28 volts, okay? And that's close to the band gap of silicon, about 1.1 electron volts. So at this very low temperature, the voltage needed to push an electron around the circuit is about 1.028 electron volts per electron. However, at room temperature, the voltage was lower. All right? I've taken the diode out now. It's warming up. And you can see the threshold voltage is getting smaller as the diode heats up. I'm going to heat it up in my hand to accelerate this process. And then pretty soon we'll be back down to the value at room temperature. Okay? There we go. Okay, well that's what I wanted to demonstrate for you. Here, one sec. Okay, well to understand why the threshold voltage gets smaller, we need to include a little thermodynamics, all right? So in particular, we have the first law of thermodynamics, which expresses energy conservation. And it says that the change in the energy of any system is the sum of the work done on the system plus the heat that enters the system, okay? So that in this case, the work done should be equal to the change in the energy of the system minus the heat that enters the system, okay? In our case, the work done per electron we're calling delta mu, and this is equal to the band gap, that's the change in the energy of the electron, minus another term. And according to thermodynamics, since the system remains at constant temperature throughout the process, this term is T times delta S, where T is the temperature and delta S is the change in the entropy. Due to adding one electron on the n-type side and adding one hole on the p-type side. Remember, when we take the electron around the loop, we add an electron on the n side, but we've taken away an electron on the p side, so we've added a hole. Okay? And it turns out that rather like a expanding gas, the entropy of the electrons and holes in the semiconductor increases. Rather like an expanding gas, when electrons and holes enter the semiconductor, their entropy increases. Okay, that's what I wanted to say. And because the entropy increases, this term becomes important. And what it means is that when the electron and hole enter the semiconductor, a little bit of heat flows into the semiconductor from the environment in order to keep the temperature constant. And this heat supplies part of the energy required to bring the electron around the circuit. In a way, the diode is actually, a forward bias diode is actually like a refrigerator, okay? Not a very effective one, but as we pump electric current around the circuit, a little bit of heat flows from the environment to keep the diode at constant temperature. All right, so that sets the stage. We'll look at this in detail in the next video, okay?